Okay.
So our next speaker is Jason Wang from Caltech. He will be telling us about early science results from the Keck Planetary Imager and Characterizer. And just a second, let me start and stop the timer so I don't shortchange you. Go ahead.
Thanks. Great, thank you. Yeah, so today I'll be talking about some of the first science results coming out of KPIX. So before I begin, I'd just like to acknowledge that all of this was made possible with a large instrument team that has made KPIX happen. It's been led out of Caltech by the PI Dimitri Mawei, but you can see it's quite a large international collaboration of people that have contributed to KPIX. In particular, I'd like to acknowledge our funding sources, NSF and Hiding Science Foundation, as well as Caltech and JPL. So the first question you might have is, what exactly is KPIX? Is this a new instrument? What is it? We've been talking about it as a new instrument, but what it actually is a series of upgrades to the Keck 2 AL system and instrument suite. So here I have a cartoon layout of Keck 2. So you can see the primary mirror here. You have the deformable mirrors for the AO system here. And this is the regular facility natural guide star wavefront sensor. This is what's in Keck already. And usually this feeds the NERC2 imager, but what we've added is this infrared pyramid wavefront sensor. So we can take some of the H-band light, feed it into here, and do our wavefront sensing in the infrared resident visible. This is really great for red stars, especially like M dwarfs or young stars harboring protoplanetary disks. If you're interested in more about this, check out Nicole, Bin, and Tai Chi's posters on doing KL and M-band chronography with KPIX using this new pyramid wavefront sensor. But what I'll be focusing on today is this really novel capability in which we actually steer the light from the AL system into what we call the fiber injection unit, or FIU, which feeds that light into a single mode fiber that gets fed into the NIRSpec high resolution spectrograph. And what this allows us to do is to do K and L band spectroscopy at R of 35,000. And in particular, it allows us to do this on directly imaged exoplanets. So we're able to combine high contrast imaging with high resolution spectroscopy together. And lastly, I'd like to mention we also have some new interesting KPIX hardware. Check out Kent's poster on Zernike wavefront sensing. That's also something that we're looking to implement currently in KPIX. So for the bulk of the science results we talk about today, we'll be focusing on the HR8799 system. This is a directly imaged system of 4 super Jupiter exoplanets. So you can see here is a time lapse from Keck of 7 years of these planets in orbital motion. You can see the 4 planets here. They have masses somewhere between 5 to 9 Jupiter masses. They are orbiting somewhere between 15 to 70 AU. And what you might not appreciate from these images is that these images are heavily processed and require about an hour to generate each of these frames. So these are heavily post-processed images. What you see from the raw data from Keck is actually something on the left here. This is a single chronographic image of the HR8799 system. You can see the star behind the chronographic mask. But all the other light here you see is stellar glare. This is residual starlight that's somewhere between a factor of 10 to 100 times brighter than any planet in the image. And this is one of the key challenges of KPIX, was actually placing our single mode fibers at the location of these planets because we can't see them. If you're interested about this technical challenge, please ask me about this later, or we're happy to discuss this with you on Slack. But we figured it out. We're able to basically blindly offset the fiber to the correct location to within 10 milliarc seconds of the planet. And basically what we have is a fiber array. We place one of our fibers at the location of the planet. It injects in planet light, but also residual stellar light contamination. But we also have multiple other fibers that we can place along the focal plane to observe just starlight. So what you see on the NIRSpec spectrograph is something like this. So I've shown 2 of the orders here, and you can see 3 of the fiber traces. So this top trace is the star plus planet trace. So this trace contains light from both the planet and the star. And the other 2 fiber traces contain starlight only. And with these starlight only traces, we're actually able to calibrate out the starlight to basically isolate spectrally the light of the planet. So we had a few early science runs this summer, and I'd like to thank the Keck staff for despite the pandemic and everything, to really make this new instrument work. And we've been rewarded with the first detections of some of these HRA 799 planets. So this is the first detections of the inner two planets, HRA 799 D and E, at high spectral resolution at R greater than 10,000. So you can see here the cross correlation functions. At the correct radial velocity, you see a peak in the cross correlation function with an SNR about 10. So being able to detect these planets, especially the inner two planets, really demonstrates the high contrast capabilities of KPIX. Never before could we do this because the stellar glare was just too bright, but because of the new technologies in KPIX, we're able to do this. And also we're able to detect HRA799C, which has been detected before with NIRSpec, but we've been able to do it with 2 times better SNR with 4 times less exposure time, to show you the benefits of KPIX over previous generation of high resolution AO-fed spectrographs. One thing I just like to mention is that we have a unique capability to calibrate out the starlight. So we're actually able to forward model our data completely. So here in black, you can see the data on the HRA799B, and we're actually able to generate a forward model of the data in teal, and I've decomposed that forward model into blue, which is a stellar model, which we observe used simultaneously using our star-only spectrus fibers. And we're then able to fit planet atmospheric models to the data in red, even though it's a factor of 10 to 100 times fainter. And this allows us to obtain many properties of these planets at high spectral resolution, many of which have never been obtained before. We've measured their orbital velocities that are consistent with their orbital models of their orbital motion. We're able to detect their spins for the first time ever. This is the first detections of the spins for HRA799 D and E. They correspond to rotation periods between 3 to 6 hours. And lastly, we're also able to start studying their atmospheric properties at high spectral resolution and study their composition. Lastly, I'd just like to mention that KPIX phase 2 is coming soon next year. We're going to add a series of upgrades to even further improve the high contrast capabilities of KPIX, and all of this improvements in the hardware will then be basically fed into this new high spec spectrograph that Dimitri has a poster on, this new AO-fed infrared spectrograph for Keck. So yeah, that's all I have. So here at KPIX, we've demonstrated the first detections of the high contrast directly imaged planets. And I just encourage you to check out the KPIX posters that we have here at the meeting today. Thank you.
Thank you, it's beautiful. Wait for questions to come in. I will take the first question very quickly. Roughly what magnitude stars are you able to look at?
Yeah, that's a great question. So we're limited by the infrared wavefront sensor. We're down to H of 12. So anything brighter than 12th magnitude in H. Awesome.
And if the SOC, I see questions come in, I think slightly slower. There we go. Thane Curry had a question. What is driving the higher temperatures for HR 8799 versus previous results?
Yeah, that's a great question. I think this is actually to deal with the models themselves rather than the data. I think at high spectral resolution, favoring these higher temperatures might be the fact that we think that these planets are in disequilibrium chemistry. That even though their broadband SEDs might favor lower effective temperatures, that the fact that they're in disequilibrium chemistry might favor these models, which are assume equilibrium chemistry, to actually favor higher effective temperatures from just the high-res non-continuum data alone.
Great, and we have one more question. We have time. Philip Hines asks, can you constrain the composition of HR 879 planets with these spectra?
We think we can. It's current work in progress. We attained these spectra just 2 months ago, so we're still digesting things, but that is the ultimate goal. Yes.
Awesome. And Andrew has a question, since he's on the SOC, that's supposed to happen. What sets the precision on V-Sin measurements for directly imaged planets?
So it's partially set by the signal noise and partially set by the resolution of the spectrograph. So I think we're only sensitive to several kilometers per second rotation rates. Anything below that, we wouldn't be able to detect from the resolution.
Awesome, thank you.